Welcome to our next video on condensed matter theory. In this video I would like to discuss with you the problem that we have in writing down n-particle basis states, when in the next video we will then talk about the solution. We've seen in the previous videos that quantum mechanics scales exponential with system size, and that is the number of basis states that we refer to in this case. What I want to talk to you about in this video is that not only the number of basis states scale exponential, if we write down our basis states as wave functions, then also the number of terms in each wave function scales as a faculty of the number of particles that we have in our system. Where the first problem is not simple to solve, the writing down the basis states, your Slater determinants or wave functions, you can solve by using second quantization. And that's what we'll introduce in the next videos, or repeat if you've already seen it in the language that we will use and in the notations that we will use during this lecture. So let me first explain to you why we have this scaling before we, in the next video, then show you what the solution is. And the state is that if you write down an arbitrary wave function, if you write down a wave function that is actually a solution of the Schrödinger equation, then with a high probability that wave function is not realized in nature. Actually, only a tiny fraction of all possible wave functions that are solutions of the Schrödinger equation or Dirac equation or quantum electrodynamics, so that's not where the problem is a solution. Also, possible solutions of the Schrödinger equation are realized in nature. And the reason for this is the Pauli principle. So, what Pauli postulated in order to explain the periodic table that we see behind us is that any two particles must be in a different quantum state. And with that, we're going to restrict a huge number of possible solutions from the Schrödinger equation. So let's have a look at possible solutions for helium. As we can see, helium has 2 electrons in the 1s orbital in our periodic table. So without the Pauli principle, we find 4 solutions of that form. We have 2 coordinates, R1 and R2. And we can either have an 1s electron with spin up at coordinate 1, or an 1s electron with spin down at R2. We can have an 1s electron with spin down at R1 and spin up at R2. These two wave functions are orthogonal to each other. If we calculate the inner product of an 1s electron with spin up and a 1s electron with spin down, and we integrate over coordinate R1, that is definitely going to be 0, so these are independent two-particle wave functions, and both solutions of the Schrödinger equation on the level of approximation that we have, where we say we have 2 electrons in the s orbital. And then of course we can make one wave function where both electrons are in the same spin orbital, both spin up, or both spin down. So the Schrödinger equation has 4 solutions for the helium atom, and it truly has 4 solutions of the helium atom. Now the Pauli principle restricts to because these two wave functions obviously have two electrons in the same state. That said, it still leaves two possible solutions for the ground state of helium. And from experiment we know that the ground state of helium is single-fold degenerate, so this would not be in agreement with experiment. So we somehow have to precise the meaning of two particles cannot be in the same quantum state, they have to be in different quantum states to make sense of having these two wave functions that are still available. And one thing that is very important to realize in physics is that physics must be basis set independent. And for our spin, that means that we can either quantize the spin direction in the x, or in the y, or in the z direction. And in the end we should always get the same answer and the same physics coming out. We can make basis set transformations, and a quantization in the z direction is equal to square root of half spin up in the x direction plus spin down in the x direction, and its state with spin down in the z direction is equal to square root of a half spin up in the x direction minus spin down in the y direction. So that's a unitary transformation going from quantization in the z direction to quantization in the x direction. So now let's have a look what happens with our definition of two electrons must be in different spin orbitals when we put on a basis transformation. So we're going to say we start with a quantization in the z direction, and let's put in these equations to see how our wave function looks like if we quantize in the x direction. And what we find is that the 1s up in the z direction, 1s down in the z direction for coordinate r1 and r2 is equal, we can just put in these two wave functions, square root of a half x up at r1 plus x down at r1 times square root of a half for the second one, 1s x up or spin up in the x direction at r2 minus the spin down quantized in the x direction at r2. If we write this out, square root of a half times square root of a half is a half. Then we have here an up times up at r1 psi 1s up x at r2. We have a down times down with a minus sign, spin down in the x direction at r1, spin down in the x direction at r2, and then we have a minus up down and a plus spin up in the x direction times spin down in the x direction at coordinates r1 and r2. By the Pauli principle, these should not be allowed. So this state that looks as if these two particles are in different orbitals, which the Pauli principle tells us they should be, after a basis transformation you see that that wave function has some part where your particles, your electrons, do occupy the same orbital. So these terms are forbidden by Pauli, and what is left is a fully antisymmetrized wave function. And it turns out that if you take a fully antisymmetrized wave function and you do a basis transformation, a unitary basis transformation, that stays fully antisymmetrized, and for that we have only a single solution, which is the fully antisymmetrized wave function. So the Pauli principle that states two particles must be in different quantum states translate to the mathematical requirement that our wave function is antisymmetric in coordinates. And this is the classical alternative to the statement that two particles cannot be on the same place in the same time. Now if we want to write down our wave function, not for 2 electrons but for 3 or 4 or many, then we can realize that we can generate fully antisymmetric wave functions with the use of Slater determinants. So a 2 electron wave function, let's write down the one for helium with 2 coordinates, R1 and R2. They're all vectors up to now, so I started with vectors but then I dropped my vector at some point. Can be written down as a determinant. We have to normalize by the number of terms that we have in our determinant, and then we have a determinant of a matrix where we have the 1s orbital with spin up at R1, the 1s orbital with spin up at R2, the 1s orbital with spin down at R1, and the 1s orbital with spin down at R2. And if we take the determinant, it's this one times this one minus that times that one, and that's exactly what we had before. We can do this general for an n-particle system. We have to normalize by the number of terms that we have, which is the square root of n faculty. We have n faculty terms in our wave function, and we take the determinant psi1, r1, psi1, r2, up to psi1, rn, psi2, r1, up to psi-n, r1, up to psi-n, rn, and the determinant. So this one times the determinant of what is left, this one times the determinant of the minor, etc. And then you go down until you have n faculty terms. So for n electrons in n one-particle basis states, small n basis states, we saw in a previous lecture that we have small n over capital N, and this is equal to small n faculty divided by capital N faculty, small n minus large n faculty, n electron basis states. That's a large number. That's where the exponential scaling comes, and that makes quantum mechanics hard. But if I now want to write down a single n electron basis state, that basis state has n faculty terms. So when I want to calculate an integral between two basis states, of which I have exponentially many, I have to take n faculty terms times n faculty terms of the other state. So it's not only that we cannot write down the complete Hilbert space of our n-particle system, we cannot write down even a single term or a single state in this many-particle system, just because each state has n faculty terms. Now the later problem is solvable when we go from wave functions to second quantization, where we put this antisymmetric wave function into the operators that we use to describe our system, and we start talking about creating or annihilating these particles out of the vacuum. And that's what I want to discuss with you in the next video. So here we laid out the problem. We cannot write down our single particle basis states if we use wave functions. And in the next video we'll show you how to solve this. At least this is easily solvable. And that's the language that we will use and continue to use, and is also what then naturally reads into quantum field theory and all the Green's functions that you can use in other lectures. With that, thank you very much for your attention. Stay healthy. We see each other later.